Throughout this lesson, we are going to investigate temperature and demonstrate its importance to meteorology. Temperature is a measure of the heat energy derived from the agitation of molecules. The higher the energy the molecules have, the greater the agitation and the higher the temperature. Temperature can be measured on a variety of scales using many different instruments. The two most common scales we use to measure the temperature of a substance are Celsius, sometimes called centigrade, and Fahrenheit. The Kelvin scale of absolute temperature is rarely used in general aviation meteorology, but you may see it in scientific formulae. At absolute zero, or 0 degrees Kelvin, all molecular activity has ceased. However, Celsius is the scale we use throughout the CD-ROM where appropriate. You may be required to convert from one temperature scale to another. To convert Fahrenheit into Celsius, simply subtract 32 from the Fahrenheit value and then divide it by 1.8. To convert Celsius to Fahrenheit, simply multiply the Celsius value by 1.8 and add 32. You will also find a conversion scale for Fahrenheit and Celsius on your flight navigation computer as shown here. Finally, to convert Celsius into Kelvin, simply add 273. The instrument used to measure temperature is called a thermometer. In meteorology, thermometers which are used to measure the temperature of free air are usually housed in a Stephenson screen. These are located 4 feet above ground level, allowing the free passage of air through the housing, but preventing direct exposure to the sun's radiation. However, there are many different types of thermometer. The one shown here is a thermograph. It records temperature over time on a rotating drum. Let's now consider the practical implications of temperature in the atmosphere. Energy from the sun, or solar radiation as it is called, has a short wavelength. The Earth's atmosphere is actually almost totally transparent to this incoming shortwave radiation. The incoming energy passes through the atmosphere with little effect, and therefore does not appreciably warm the atmosphere. Only when solar radiation encounters clouds or reaches the Earth's surface does it have an impact. Clouds will reflect part of the incoming energy out to space again. The rest will continue to the Earth's surface. In clear weather, around 85% of the original energy from the sun will reach the Earth's surface. At the surface of the Earth, the sun's energy has its greatest effect. Incoming shortwave solar radiation, or insolation, is absorbed by the Earth's surface, and as it does so, the surface warms up. The Earth now acts as a heat source, continually radiating its own heat energy outwards. Heat energy emitted by the Earth is a lot less intense than the sun, and it has a relatively long-wave radiation. The atmosphere absorbs the heat energy from the Earth's surface by various means. The fact that the atmosphere is heated from below and not from above explains why within the troposphere temperature generally falls with increasing altitude. So what happens to this energy as it is emitted from the Earth's surface? How does it heat the atmosphere? The most important process is where two of the constituents of the atmosphere, water vapour and carbon dioxide, absorb this long-wave radiation from the Earth. The Earth then acts as a heat reservoir for the atmosphere, warming it up to a greater or lesser extent, depending on whether it is day or night, summer or winter, cloudy or clear. The way in which the atmosphere allows solar radiation to pass through it to the Earth but is then heated by long-wave terrestrial radiation, is referred to as the greenhouse effect, and without it the Earth would cool dramatically. There are other methods of heat transfer, and we shall look at these in turn. Conduction is the simple process whereby heat is transferred by direct physical contact between two bodies. Looking at the diagram, you will notice that during the day, the lowest layers which are in direct contact with the Earth are the warmest. However, during the night, as the land cools, notice that the air in contact with the land also cools, leaving a typical nighttime temperature profile as shown. The next process we are going to consider is convection. This is defined as the process by which masses of warmer air are raised into the atmosphere with compensatory downward movements of cooler air. Because of unequal heating of the Earth's surface, warmer, less dense air will rise relative to the cooler, heavier air on either side. This cooler air in turn will sink. On hot summer days, this movement is visible through the presence of large vertically growing cloud developments called cumulus clouds. Some of these may grow up to the tropopause, transferring heat high up into the atmosphere. Another process of heat transfer is advection. This is similar in principle to convection, but the transfer of heat takes place on a horizontal plane. If the warm air is rising, cooler air will move horizontally to replace the rising air. This movement of cold air is called cold advection. Finally, the last method of heat transfer is through the absorption or release of latent heat. This is where heat is liberated when a substance changes state without any change in its temperature. If condensation occurs, water vapor is converted to water droplets. This process, which occurs in clouds, actually releases energy in the form of latent heat into the surrounding air. Conversely, if evaporation takes place, which is when water droplets change to water vapor, latent heat is absorbed from the air. The rate at which temperature falls is called the temperature lapse rate. We have already seen that generally temperature decreases with altitude. This is otherwise known as the environmental lapse rate, or ELR. You may recall from earlier lessons that ISA stated that the average environmental lapse rate was 1.98 degrees Celsius per 1,000 feet, often rounded up to 2 degrees Celsius per 1,000 feet. However, under various conditions, the environmental lapse rate can and does vary significantly from this average. If the temperature remains constant through a given depth of atmosphere, we describe it as being isothermal. This is shown here. You may recall from the lesson on the atmosphere that the tropopause is a place in the upper atmosphere where isothermal conditions prevail. We can actually find temperature increasing with altitude. This is because the surface layers are cooled by the Earth, but the upper layers, being further away, are not affected. This temperature increase with altitude is called a temperature inversion. The variation of temperature across the Earth is an important aspect of meteorology. This variation can arise from the daily and seasonal influences of the sun, the nature of the surface, the latitude, and so on. Each of these reasons will be looked at in turn. The temperature of the air also often varies greatly in the same location through a 24-hour period. This is called diurnal variation, or DV for short. The Sun is at its highest at noon, with the maximum incoming solar radiation occurring at that time. However, due to lag, or what is called thermal inertia, the surface of the Earth continues to receive more incoming solar radiation than it gives out. Therefore, the actual maximum air temperature usually occurs some 2 to 3 hours after maximum solar elevation, usually at about 1500 hours local time. Similarly, the minimum temperature time is around half an hour after dawn. Clouds have a big influence on the maximum and minimum temperatures. You may remember from earlier lessons that we said that clouds reflect incoming solar radiation during the day, thereby reducing the incoming solar radiation. This would reduce the maximum daily temperature. At night, though, the cloud acts in a very different manner. The energy stored inside them from water vapor and latent heat release actually helps the clouds re-radiate energy back into the layer of air between them and the surface, much like a blanket. This has the effect of making the minimum temperature much higher than normal. The combined effect reduces the diurnal variation of the temperature, but the characteristics of the curve are almost the same. Notice how the maximum daytime temperature is lower with cloud cover and the minimum temperature, occurring just after dawn, is higher with cloud cover. The wind also affects the diurnal variation of the temperature. By day, the effect is to reduce the maximum temperature. This is because turbulent mixing of the lower parts of the atmosphere brings down cooler air from above, mixing it with warmer air near the surface. Wind also reduces the time that air spends in touch with the ground, lowering the amount of warming that takes place by conduction. At night, the wind keeps the temperature up, preventing it falling as low as it otherwise would. Air near the surface will cool by conduction with the ground. Look at how turbulent mixing then brings the warmer, unaffected air down from a higher level, averaging out the temperature through an appreciable depth of the atmosphere. There is, of course, a large temperature variation across the surface of the Earth. There are many factors involved with this. We shall now take a look at the main ones. Take a look at this diagram. You should be able to see that when considering a unit cross-section of energy from the Sun, the same amount of energy is spread across a greater area at higher latitudes than at the equator. Therefore, any single point at high latitude will receive less energy from the Sun than a point at lower latitude. Another reason the equator is warmer is because the Sun's energy arrives at 90 degrees to the surface. This allows more efficient absorption of heat compared to the poles. These combined effects cause the poles to be significantly colder than the equator. It is interesting to note that compared to the distance between the Sun and the Earth, the slightly greater distance between the poles and the Sun compared to the equator and the Sun is negligible. Because the Earth is tilted on its axis in space, we have seasonal variations in temperature across the Earth's surface. In the diagram, you will notice that on June the 21st, the Sun is directly over the Tropic of Cancer at 23.5 degrees north. The Sun's rays are striking the Earth's surface at 90 degrees. Therefore, it is this latitude, and not the equator, that is the warmest. The diagram shows the summer season in the northern hemisphere and the winter season in the southern hemisphere. However, on September the 21st, notice that the solar radiation is striking the equator at 90 degrees. This is called the autumnal equinox. On December the 21st, the Sun lies directly over the Tropic of Capricorn, which is 23.5 degrees south. The diagram now shows the summer season in the southern hemisphere and the winter season in the northern hemisphere. On March the 21st, the Sun is directly over the equator again. This is called the vernal equinox. The sea takes a long time to react in terms of warming and cooling. Here we see that there is very little diurnal temperature variation of the sea when compared to the land. This is because the sea has a large specific heat capacity. This means that the sea requires more energy to raise the temperature by 1 degree than the land does. This effect is noticeable daily and seasonally. During the day and in the summer months, the land will be hotter than the sea. But during the night and in the winter months, this situation is reversed. The sea will generally be warmer than the land. This difference in temperature over the land compared to the sea is the cause of such things as sea breezes and land breezes. These will be looked at more closely in the lesson on winds. Throughout this lesson we have concentrated on how temperature is measured and, more importantly, how it varies across the Earth. This variation plays a very important part in the creation of weather. Next, though, we will look at the types of pressure systems and their associated weather.